changes.
Life. Life.
Tell me like a Hellcat. Coming like a Hellcat. Like a Hellcat.
Good evening, everyone. Hope you're having a great weekend leading up to the, we're well and truly in the thick of the silly season now. It's been a while since we hung out. Last Sunday, I was at a family friends thing that we do each year, a Christmas get-together. Wednesday rolled around, and Wednesday afternoon, I was just feeling super worn out, burnt out, and didn't feel like streaming. And I didn't think that you fine people deserve to be put through me being grumpy and doing a half-assed stream, so we had the night off on Wednesday. This, I've decided, will be the last stream for this year. I would like the chance to have some downtime over Christmas. I've got a lot going on, and let's recharge the batteries and kick it strong in 2017. So I hope you enjoy your stay tonight, Please, as always, get involved, ask questions. This is really what we will make of it. So I'd love to hear your questions, queries, concerns, comments. We can go on stream, we can go on topic, off topic, whatever. All fair game. Let me know if the music is too loud, if the voice is too quiet. We can fix audio visual issues if needed. I'm always paranoid that I can't be heard. If you were around a week and a half ago, would have been about a week. Yeah, would have been a week and a half ago. We did the shitsco challenge from DEF CON 22 quals. I should probably move that. I didn't have anything on that window that I shouldn't have been showing. That worked out quite lucky. Let's get rid of that one. We exploited a info leak in the. Let's open up the IDA database that we were working on. If you missed it, what we did was ended up exploiting. Where was it? In Funk. Oh, is this like a half-assed... Did I not save the IDA? I probably didn't save the IDA database properly. Okay, we get to go back through the IDA database and fix stuff up. There was an info leak in... Let's see if we can get it up and running. Twitch, shitsco. Run the binary. Failed to open password file. Oh yeah, when you run this binary, it goes and looks at a hard-coded path in /home somewhere. Strings window. Yeah, it looks for the file home shitsco password, and that's the password that's used to authenticate some stuff. Actually, what we should probably just run through a quick demo of the kind of stuff that the binary does in case you missed it last time. So we need to make sure that this file exists on disk. As always, I'm working in a Docker container so that I don't go and accidentally show too much personal stuff on stream, because that's always fun when that happens. So what we did last time is I just made a directory /home/shitsco and then dropped the password file in it. Bit of a different one this time. Let's just symlink from Justin to shitsco. And what this should do is let us look inside shitsco. You know, we can go ls/home/shitsco. And from the point of view of anything accessing it, it will just be a mirror of our own home directory. And we'll just go and drop a password file, echo-n, the password, into the file called password. And we should now be able to run the binary. So we'll jump into twitch/shitsco and run it. And there we go, now we get the binary behaving. So it looks like it's a send off of the Cisco iOS kind of prompt. We can whack ? Oh, we've got people dooting me. Still waiting for the accidental reveal of, I'm not going to repeat what Parks just said. Yeah, Beator 010 editor is great. It's good stuff. It is awfully specific, isn't it? Parks might need to time himself out for a minute for that one. Please, if you're wanting my attention, if you've got any questions, queries, concerns, go and drop my full name, the Justin Stephen, in chat. That way this chat window actually lights up and I know that there's people summoning me and my attention, and I will attend to your queries. So yeah, please use my name if you need my attention. So the binary, we can enter ? and get a help menu. We can do ping, and you've got to specify an address, so we can go 127.0.0.1, and it'll ping localhost. We get a tracer-t command. If you actually go to the help for trace route, but tracer-t shows how many hosts are connected to a machine. If that Easter egg is not familiar to you, go and look at the tracer-t tutorial on YouTube. It's a cracker. We've got commands like credits. We've got NextGen Hacker 101's probably the person who uploaded that YouTube video, I reckon. We get some other stuff. We get shell, this lovely troll. Looks like it gives you a shell, and you can type ID, and it kind of hangs, and then it says, yeah, right. We can set stuff. We can set foo to bar. We can show all the variables. We can show foo. It'll show us what foo is set to. What we exploited last time was enable. Now, enable, if you're familiar with Cisco routers, when you connect to a Cisco router, you get a pretty unprivileged prompt at first, and you need to type enable and then enter the enable password to become the local super user to actually do certain things on the Cisco device. It asks you for a password. We'll put in a couple of capital A's. Comes back saying, nope, the password isn't a couple of A's. Oops. A. Depending on how many A's you put in, sometimes you get some trailing garbage in this response here. So what we should do is we should go and have a look in IDA at how this function works. And we know that this function, this binary, we found out last time that there's this dispatcher function, which does a whole bunch of horrible stuff. And if you look down, I think about here-ish, there was an indirect call to some location. And this really stuffs IDA's idea of functions up. Sometimes it doesn't recognize certain bits of code as actually being functions, and it doesn't actually show you the functions in the list here. So we need to dig through the code and actually tell IDA to go, this is a function, this is a function, go and actually show them to us as if they're functions. We need to help IDA out with doing its job a bit. And we know that there's a function to do with please enter a password, nope, the password isn't blah, to do with basically authenticating access via the enable command. So if we go in IDA and have a look at the strings menu and have a look at for the strings, please enter a password, or nope, the password isn't blah, then we should, let's filter this for password. Whoop, that's not what I wanted. Here we see that these two strings in the binary are known to IDA. So we can go to the first one, please enter a password. We can click on the label that IDA has given this offset in the binary. Press X for cross references, and we can jump to the part of the code where that string has been referenced. You can see it's referenced here, and IDA is showing us that these addresses within the binary, that it's showing it as red, which I'm pretty sure means it's not belonging to a function. So we should be able to have a look through here and actually mark something as a function. So we've got a return here. We've got some stuff to do with authentication successful, and then a jump back up to here. So I reckon this here is probably, I think it's the same function but different function. So this here looks like the beginning of the function that actually does the authenticating. So can we mark, how did we do this last time? Create function sounds good. There we go. Now we can actually look at it in the graph view and have a look at how the function works. So what we exploited last time. Got Twitch yelling at me about something. Beator's hosting me. Thank you, Beator. Appreciate it. So yeah, this is the function we exploited, and we know that there's what's called an info leak happening within this printf, where it comes back saying nope, the password isn't blah. If we have a look at the execution that we did previously, we can see that we sometimes get nope, the password isn't the password we gave, and then some trailing garbage, which suggests to me that when we supply this password, the password gets written in, or read in and then written to memory, and it's not getting null terminated. So can we see? So we've got this printf of the please enter a password. It's flushing stood out. Yep, it's flushing stood out, and then it's calling this function here, which probably reads in the password. Yep, we can see a call to read. Yep, so that looks like it's reading user input. So I'm going to rename that to get user input. I'm guessing that's what this function does, without going too deep into the mechanics of it. So we call get user input, and we're probably parameterizing this call here with the first argument 0, probably the file descriptor from which to get this user input. File descriptor 0 is standard in, We've got a parameter going on. There's no EBP for this function, so I'm going to mark it as not a base pointer based function. Oh, it's not marked as that already. Okay. So we're moving ESP, we're moving EBX to an argument. EBX currently holds the address of a ESP plus 18, which is going to be a local variable. So, I'm guessing this get user input is writing the gotten user input to this local variable. I'm guessing get user input is also not null terminating the string, which then when we go and pass to printf, the arguments, nope, the password isn't %s. %s will then be coming from EBX, which is still that pointer to where the gotten user input was written to. This will be a non-null terminated string, and so this printf will leak to us a whole bunch of stack data. What we ended up exploiting last time, we're getting there, I keep saying what we exploited last time, but there's always a bit more to explain, was the fact that the location at which we being held in EBX, we're writing to ESP plus arg14 as a local variable, which is an OX20 byte buffer that butts right up against arg34. And if we look at where arg34 is referenced elsewhere in this function, we can see that the output of the strcomp was being stored in arg34. So strcomp is being used to do a string comparison of the offset s1 is a global variable in .bss that holds the enable password. So we'll rename this to enable password. It's doing a strcomp of the global enable password, which at runtime will hold a copy of the password, which I think we set to be the password. But due to the fact that this function is buggy, we actually need to pass a null byte in, which I can't do at this prompt here. We'll have to do it from Python in a second. It's doing a strcomp between EBX, which is where we end up writing, or a pointer to the place at which our gotten user input was written, does a strcomp between these two values, and strcomp returns, what does strcomp return? The strcomp and stern-comp, we're talking strcomp, they return an integer less than, equal to, or greater than 0 if the two strings which we're comparing are found to be less than, to match, or to be greater than each other. So, based on the fact that we can end up leaking the return value of strcomp, lets us put in a password of a bunch of lowercase a's, and then we can leak the output of the strcomp of a bunch of lowercase a's against the actual password. Then we can set a whole bunch of lowercase b's, or not a whole bunch of lowercase b's. We were sending a lowercase a, then a whole bunch of hex ff, and then b, then a whole bunch of hex ff, and then c, then a whole bunch of hex ff. We could have done a binary search, but I was feeling lazy, and we could eventually see that, for example, when the password is set to the password, that the output, the return value of strcomp, which was being leaked to us, would change from a number less than 0 to a number greater than 0. And we could basically divide and conquer and brute force the password one character at a time, having info leaked the output of strcomp. And we wrote an exploit, which is this here, which is a horrible exploit. Twitch shitsco. What it would do is start off with a password of empty string, and then for password character in the range up to max password length, it would build a string. I don't really want to explain my horrible Python. Okay, we're doing it. It would build up a password string that would be password char in range that. Okay, so this for loop here is the brute force of each character one at a time, because we know that the password can only be OX20 characters long. This was my way of saying, hey, that we're going to loop through OX20 times. And then for for X in blah. Okay, so we would brute force, as part of our brute force, for each character at the beginning, we would basically loop through I, which would be every character, every possible 1-byte character, except for null bytes, spaces, and new lines, because they were found to interrupt the flow of this function, and so hence couldn't really be valid password characters anyway, so we'd skip them because they would mess with us. And what we'd do is we'd then build up a candidate password. We'd start it with the password we know to be true so far, which starts off as empty string, but we eventually end up appending to password every time we get a character correct. So we'd start off with the password that we've brute forced so far. We'd append the character that we generated in this loop, or not in this loop, in this statement here. And then we'd just pad the rest of the password out with a whole bunch of hex FFs to take us out to a total length of 0x20, so that we could then leak, because we're filling up this argument here, we could then leak the output of this using the printf. And hex FF was a good choice because it let us make the most of the info leak and the whole less than or greater than behavior of strcomp. We'd send that down the gullet of the program. We'd go and receive the response, which would say, no, you got the wrong password. The password is not, a whole bunch of FFs with a bit of magic in the beginning, and then it would leak to us either a number less than or greater than 0. And then based on what we got, that leaked integer that we got back, if it came back as being less than 0, we'd know that we had just discovered a new character of the password, and we'd append it to our password string, and we'd print out kind of a gradual success message that would gradually show us more and more of the password being leaked. And then it would try the password we'd leaked so far to see if we then got authentication successful. And if we did, then we'd print out a happy face and say that we'd gotten the password. It would return the password back to the caller of this getPassword function. And this code down here is like freak out because something's gone wrong. We should never have reached that part of the code if the whole brute force was working properly. So then my exploit basically just connects. We spin the binary up in G. Oh no, we spin the binary up here. We attach a debugger. We eat the prompt. We define our function. We call our function, and then we just return an interactive little shell with the binary. So what we need to do, I think, is actually null terminate the password as it's stored on disk. So if we have a look at that file now, we can see that it is the password and then null byte. So that's so the strcomp would work properly. I think that's required. So if we ran the exploit, then we can see that it very gradually builds up the password, brute forces it one character at a time, because brute forcing a password one character at a time, rather than brute forcing the entire thing all at once, is a lot quicker. It becomes a divide and conquer problem. So then we'd get a little happy face that say that we'd found the password. It is the password. And then we get switched to interactive mode by our exploit, and our exploit actually drops us at this privileged prompt. And when we're at the privileged prompt, we get a new command, which is flag. If we run flag, then we get the flag if the flag file had actually been created. Where is the flag file? I'm guessing it's in home shitsco password. Flag. It's not what I wanted. Yeah, so home shitsco flag. Let's go and put a file there real quick. echo-n flag the flag to /flag. Now if we run flag again, yeah, we get the flag is flag the flag. So that was what we did last time. I spotted this info leak bug pretty early on in the night, and then proceeded to ignore it, and went and pounded on the set and show functions, which you can do stuff like set food to bar. You can show all the variables that have been set. I was pounding on this here because that seemed like interesting functionality. I mean, the info leak I saw, I was like, oh, that's pretty cool. We might need that later. And then ignored it, not realizing the power of it, not realizing that the info leak was leaking to us the output of the stir comp, which if I'd realised earlier in the night would have shortcut a lot of the pain. But that was the watershed moment right there, seeing that. And it was Mongo who eventually put me back on the right track and told me that, hey, you've already found the bug, stop playing with the set and show stuff, go play with the info leak. So that was very much appreciated. However, once I finished the stream up and spoke to OJ was like, oh, hey, how'd the challenge go? Because OJ picked this challenge for us to do. He thought it was a cool one, and I agree it is a cool one. He said, how'd you go? I said, yeah, good. I ignored the bug for a few hours, and then Mongo told me to look at the bug, and then I did it, and then I did the thing. And OJ's like, yeah, cool. Did you find the use after free bug? And I said, there was a use after free bug? He's like, I think so. I think I saw someone had a write-up that had a use after free bug. Did you not exploit use after free? I said, I didn't exploit use after free. And he goes, hang on. I said, can you go and read the write-up and make sure there's definitely a UAF? Then a couple minutes later, he goes, yes, there is a use after free bug. There must be 2 bugs in this binary. So I think, we're on the right track by playing with the set and show stuff. Because OJ said that, and disclaimer, I haven't read any write-ups at all. I then dived back into the binary, and within about 5 more minutes of throwing silly stuff at the set and show functions, I got some weird behavior triggered. And then thought, cool, we can, I'll stop now, and I'll forget what I just saw, because it was a couple of weeks ago. I think I remember-ish, sort of what I was doing. And I thought tonight we would dive in and see if we can find the second bug, the use after free bug. So I don't know what we're in for. I don't know if it's easy or hard to find, but I'm told there's one there. I have seen some weird behavior come out of this binary, and let's give that a go, hey? What have I missed? What have I missed in chat while I've been waffling on? Is this the Tracer T? Yeah, cool. Yeah, it's a classic, that one. It's one of my favorites. Indeed we are. Thanks, Parks. Is it C? Lockdown, how's it going? No, we're not making a botnet tonight. We're beating up on a CTF pwnable. It's an intentionally vulnerable binary. We're going to find bugs and write exploits. Is it C? Yes. The program would have originally, almost 100%, have been written in C. Then it got compiled to a Linux binary. And so what we're doing here is, if you're not familiar with this, this is a program called IDA. It's the interactive disassembler. What it does is it takes compiled binaries and breaks them down into assembly, and gives you a whole bunch of really nice UI tools that I don't understand a tenth of what I should. I don't know how to use the tool, but I make the most of it. That helps you kind of make sense of what the compiled program is up to. So the challenge was published as part of a competition, and the source code may have since been published, but I haven't gone looking for it. But certainly during the competition, the source code was not made available. So you don't get to read the source code. You have to stare at this until your eyeballs bleed, or until you get so sick of looking at this that you go and buy the IDA decompiler license. Unfortunately, IDA is expensive. The IDA decompiler plugin is even more expensive, but the decompiler plugin would turn this into a C-like pseudocode sort of thing. But because I don't have that license, we have to look at the disassembly. So it was written in C, but yeah, we're looking at the assembly now. And Python, thanks Bitor. This here is my exploit, which is written in Python, and I use what's called pwnable, which is a really nice Python library for making exploit development a little bit easier. Naxor, maybe. The GDB terminal splitting from pwn. Okay, so the terminal splitting from pwn.context is not working in xterm. So I don't use xterm, so if it's an xterm problem, I can't help with that. I use URXVT or RXVT Unicode. It hangs waiting for the debugger. When you say GDB terminal splitting, you're talking about tmux, aren't you, Naxor? If videos get taken down, say it's okay under parody law. Indeed. I've been speaking to Twitch. I had to take the Rick Astley remix out of the playlist because I got a YouTube copyright claim from some other remixer, or from like some media copyright infringing hunting middleman on behalf of a different remixer saying, hey, you're using this remix that's copyrighted. It's like, no, it's a different remix. So I contested the claim, and then they came back with, nope, you're wrong, you're using our remix through the automated system. And so rather than fight that one, because if I contest it again and they issue a DMCA takedown, then I get a YouTube copyright strike for no good reason. I don't want to risk that, so I just said, whatever, I'm going to forget about it. But that song is no longer in there. I'm also on the blower with Twitch. There's an NCS track that I'm having grief with, and they seem like they're looking into it. It took a little while to get through to a human there, but they seem quite interested now. Okay, cool. If you're going to expect PT malloc, what's the diff between PT malloc and malloc? Oops, don't have my little Google searcher thing set up. Okay, has the GNU library switched from DL malloc maybe? I'm not as up on all the different flavors of malloc as I should be. But okay, there's a plugin for radar. Okay, cool. Naxor, go and drop a link to that. I'd be keen to check it out and see what's going on. But Naxor, let's have a look at your tmux stuff. So if we just go Python, import pwn, let's go tube equals pwn.process sleep 6000. Okay, so I've started up sleep. If I now do pwn.gdb.attach t, I don't have xterminal emulator installed in this Docker container, but you can see that it was trying to pop xterminal emulator to actually give me GDB in a external graphical terminal. I would rather it pop as a tmux split. So what I normally do is pwn.context.up. Can't type with the microphone in my face. Pwn.context.update terminal equals tmux split w. So I update my pwn context to have the terminal be equal to a list. That list is the argv of the terminal emulator that I'm choosing to use, which is just for tmux to pop a new split. If I do the pwn debug stuff again, or pwn.gdb.attach, you can see a tmux split pops with GDB in it. I can then go continue. I can full screen this here. I can scroll GDB up and down. And I kind of get both going at once there. So that's how I use pwn-tools and GDB. I choose to set the context of pwn-tools to pop a new tmux split. So hopefully that clarifies how I manage what I manage. And if that answers your question, cool. If not, let me know. Okay, cool. I thought libc used DL malloc. No? libc DL malloc. Have they okay. Right, yeah, see, what I know of actually exploiting malloc, I don't think we're going to be exploiting malloc and free tonight. I think it's a use after free, so it's an application level kind of bug. My understanding of libc and malloc is that it used DL malloc. That's obviously a super old understanding, because the only heap stuff I can do is with super old allocators. Looks like glibc has changed to PT malloc 2, which is a fork of Doug Lee's malloc. Cool, makes sense. Thank you very much. Yes, I think that's... I don't think that's really what you want to do. So my i3 terminal... Well, I don't really have a default terminal, I don't think. But I've got mod enter bound to start URXVT. So URXVT, yeah, link, +1. Thanks, Jardeth. Naxor, if you got a link for the R2 Con Prezzo, I'd be so keen to watch that. So I pop URXVT when I need a terminal in i3. What you probably meant was to set your default terminal in Pwn Tools to Tmux, and you need to set it up with that list of argvs so that it actually splits a new window when you when it triggers. Cloud Gamers, good to have you around. Welcome. Yes, yes, there is. CCPPTT, there is a fan running, so apologies if that's distracting. If it's distracting, I'm not turning it off because it is damn hot in Brisbane tonight. So sorry about that if that's irritating. Maybe I could. No one wants to see that. No one wants to see that and have the top of my head cut off. All right, let's do some computer hacking. I reckon there is a use after free bug. Well, we know there is, and I reckon I know where it is. I reckon it's to do with the getting and setting of variables inside the program. So let's copy exploit to exploit UAF.py because we're ambitious and we name our files as if we've already achieved something. Let's get rid of these. That looks good. This all looks good. The prompt eating looks good. We don't need these. We don't need the max password length. We don't need this get password function anymore. We don't need to do enable stuff. We're just going to drop to t.interactive. So we've gutted our exploit so that it basically just starts the thing up, having eaten the prompt. Actually, you know what? Let's not eat the prompt just yet. Let's leave that. So if we now run exploit UAF, then we get down the bottom here, we get GDB running, so that if we get a crash, then we can get some information from GDB. Up here, we have the shitsco iOS. So now we need to play around with, I reckon, the setting and the getting functions, which probably allocate things on the heap and have a linked list implementation that it probably walks when you do the show. And we probably need to think of how to cause a free of something to occur in a way that we still hold a reference to it and we can still interact with it, maybe realloc it, and then interact with it through the existing handle and cause trouble. So actually we should probably go through what a UAF is before we get too excited. So if the heap and malloc and free are new to you, I'm going to give a quick 5-minute intro to the heap. From my understanding, we'll keep it super simple and we'll ignore a lot of details for now, just to kind of get enough of an understanding to understand what a use after free is. So you've got these functions malloc and free. So if we look at the man page for malloc, it just takes a size t typed parameter called size. The malloc function allocates size number of bytes and returns a pointer to the allocated memory. The memory is not initialized. If size is 0, then malloc returns either null or a unique pointer that can later be successfully passed to free. The free function frees the memory space pointed to by pointer. So free looks like this. It takes a void pointer as the only argument called ptr. So the free function frees the memory space pointed to by ptr, which must have been returned by a previous call to malloc, calloc, or realloc. Otherwise, so if it's not a pointer that came from malloc, calloc, or realloc, or if free pointer has already been called before, undefined behavior occurs. Undefined behavior is something that as exploiters we like to keep an eye out for. If we can turn that strange, spooky world of undefined behavior into something that is of advantage to us, then we become happy. If pointer is null, then nothing is done. And see, we'll ignore CLOck, and we might need to come back to realloc. Realloc changes the size of the memory block pointed to by PTR to become size bytes. So realloc lets you grow and maybe shrink previously allocated stuff on the heap. The contents will be unchanged in the range from the start of the region up to the minimum of the old and new sizes. The new size is larger than the old size. The added memory will not be initialized. When they say not initialized, they mean that it's kind of like using your disk. You know, when memory gets not wanting to be used anymore by you, unless you explicitly zero it out, it kind of just holds old garbage. So when you malloc stuff, then when it says the memory is not initialized, it could be full of garbage from previous heap allocations, which is super good for us. It's done that way for performance. You often kind of perhaps don't want when you use maybe malloc to say, hey, give me 2 megabytes of memory. You don't, as an application, necessarily want to wait for the application for the kernel to go and zero that memory out for you before it's handed to you as virtual memory. Although CLOck I think does zero, yeah. So CLOck does zero the memory. Malloc does not zero memory, and realloc does not zero memory. You can kind of end up with old garbage in there. So realloc is used to grow and shrink allocations. Now, when, as an application, you call malloc, you get back a pointer to the allocated memory. So you can ask for 20 bytes, or 20 kilobytes, or 20 megabytes of memory, and the behind the scenes action of malloc, pay no attention to the man behind the curtain. What that is actually doing is allocating data on the heap for you. So we've so far had a lot of interaction with stuff on the stack. So all these variables here, things like where the password gets where EBX gets set, yeah. Things like where the get user input wrote the response, the gotted, that's a word now, the gotted user input, that was written on the stack. As we know, the stack grows and shrinks, and as we know, the stack relates to function execution. In as much as if you've got local variables within a function, then the storage space that's used to kind of keep track of what is that local variable is holding is within the stack. And we know that stack frames live and die with function execution. Once this function here finishes executing, which we know is authenticate user, once this function here returns, if there's a return down the bottom, yep, then the stack will shrink back down to a higher memory, higher memory address, because the stack grows backwards because it's unique like that. Then, for all intents and purposes, anything that was stored in a local variable is gone forever. But the heap doesn't do that. If some function goes and asks the heap allocator via a call to malloc, hey, give me space on the heap for 20 bytes, and then malloc returns a pointer to that memory, then if the function goes and puts some stuff in the heap at that pointer that was returned to it, and then, for example, that function might return that pointer to the parent, and then that function returns to the pointer to the parent, then the parent, the caller of that function that called malloc, can go and read what was put on the heap there. It doesn't expire when functions return, unlike the stack. Stuff on the heap actually never goes away until such time as you free what's on the heap. If you don't free what's on the heap, then you get a memory leak. A memory leak is different to an info leak. So an info leak is something that's useful for exploitation. If you can get an info leak from a program, then that's where it's actually leaking data to you, as opposed to a memory leak, which is kind of, think of, you've got a bucket full of available memory, and if you punch a hole in the bucket, then you've got a leak in the bucket. Over time, as the program executes more and more and keeps on running for the next couple of days, weeks, months, it's going to slowly hemorrhage memory. It's going to request it from malloc, but then if it never frees it, then the program RAM size will just grow and grow and grow until the machine kind of becomes memory constrained, and the sysadmin gets angry because he got a page at 2 o'clock in the morning for a system that is thrashing its disk. So that's a memory leak when you don't free your shit. So you can malloc stuff, and then once you're kind of done with that data, you're supposed to call free and give free the pointer to the heap location where you had your 20 bytes worth of stuff that you don't need anymore, and then free will ensure that the area on the heap that you were using to hold those 20 bytes is up for grabs for future calls to malloc. Right? So you malloc 20 bytes, you put stuff there, you don't need it anymore. Maybe in the case of a web page you browse to, if you debug your browser and put a watch or put a breakpoint on malloc, then, except for Firefox, I think Firefox has its own heap allocator, but if it's, for example, IE, and you actually hook the Microsoft equivalent of malloc, and you go to a web page, it'll just spew allocations. Like every time there's an element on the page in the HTML, you need to malloc some stuff to hold the stuff that you're keeping track of to basically build the page. Every time you just like move your mouse on the page, it just spews malloc and free things. Like browsers are noisy as fuck when you actually watch them in a debugger. I don't know where I'm going with this, but so you malloc to put something somewhere. Oh yeah, that's, for example, when you browse from that web page to a different page, the browser no longer needs to kind of hold on to all that stuff in the heap, all the images, all the buttons, all the div tags, blah blah blah. So it's the browser's job to go and free every single one of them, because I don't need to keep that in memory unless they hit back, in which case I'll get the HTML again, I'll not realloc the memory, I'll alloc the memory again using malloc, and then put everything back where it should be. So you're supposed to free stuff when you don't need it anymore. So you malloc, put stuff there. When you don't need it anymore, when you don't need that storage space in memory anymore, you free it. The next time you malloc something, depending on the heap allocator, and there's a whole bunch of different algorithms that are basically behind the scenes for malloc and free. Those algorithms differ in a whole bunch of ways. Some of them are more performant than others, some of them are more secure than others in the event of shit having gone wrong. Some of them focus on reducing fragmentation for different patterns of allocations, so that you don't have memory with a whole bunch of little gaps in between your allocations, because that's bad because you'll run out of memory quicker. It's also bad for caching. If you keep your shit in memory closer together, then when the CPU accesses it, it can kind of cache the adjacent stuff, and you get more performant operation of your machine. So there's different algorithms, and some of them, or many of them actually, maybe I shouldn't say many of them because I don't really know how many of them work, but some of them operate what's called last in, first out. So if you free something of size OX20, then let's say you alloc 3 things of size OX20. Alloc, alloc, alloc. They're all 20 bytes big. Let's say you free the middle one. You free the second one. You've now got on the heap, because they all tend to sit linearly under some implementations of the heap allocator as well. You may or may not have them be sequential in memory. Doesn't really matter actually for use after free. But what would happen is you've got basically the most recently freed thing of 20 bytes gets put to a list of things that that malloc can then use. If you then malloc something else of 20 bytes, if it's a last in first out heap allocator, then that new allocation will be where the previous thing was that just got freed. So now we're kind of getting to the crux here. Use after free. Just like the name on the tin indicates, if you as a program free something and then use it again, that's a use after free bug. So, for example, a browser. You may have some really wonky JavaScript on a page that sets up 5 hidden buttons. And then it causes the browser to free one of those buttons because it confused it and made the browser think that that button wasn't important anymore. But the JavaScript was able to continue to hold a reference to the button. Maybe you've got a JavaScript variable that actually points to that button, that hidden button. Under normal circumstances, if that freed object had not yet been replaced, then just like on your disk, when you free stuff, it doesn't get overwritten. It doesn't get zeroed out. It stays there, generally. So if from JavaScript you used that button again and called some function on it, like toString, or get me the current label of the button, or tell me what color it is, or set the color to green, then that button, the data in memory on the heap is still there. It got freed. It's up for grabs for malloc to hand it out again, but the data's still there. So the program will actually operate just fine. It will either give you back the toString function being called on that object, or it'll change its color to green. Whatever, doesn't really matter. Where things get interesting is if, as a attacker, you can cause between the freeing of the button and the subsequent use of the button an allocation to occur which gives you control over the heap allocation that that button was at. So if you can cause an allocation of another object type that's not a button but is the same size as the button, like let's just say a string, then you may be able to go and set the string to be a whole bunch of capital A's. And then maybe when the toString function on that button is called, it made reference a pointer inside all of your capital A's, thinking it's still button data, not realizing that the button allocation got freed and you put some other shit there. It may look at a whole bunch of A's and go, oh, okay, cool. The toString function is stored at the address 0x41414141. I'm going to jump to it, or I'm going to call it. And there you go. You've got EIP control. That's super simplified. That's not how browser use after free works. It's actually, browsers are written in C++, and you've got to worry about a thing called a virtual function table that's stored at the beginning of a instantiated class or an object. So it gets much more complicated, but the principle is the same. If you can cause something to be freed by the application that shouldn't have been freed, that you can still cause to be interacted with, if you can cause an allocation that takes the same spot, think of Indiana Jones, like when you kind of pick up the little idol and you replace it with something else really quickly. If you do it quick enough, the temple doesn't realize you've done it, and then when the temple goes to use the idol, it's actually using something else, like a bag of sand. Same sort of theory. That's a use after free. You can, hopefully that if that doesn't make sense, please someone yell out, and I'll go through it again. But that's the idea. You cause something to be inappropriately freed, you replace it, then you cause the application to use what you replaced it with as if it was what it thought was there, and cool stuff can happen, and we can write exploits. vtables used to be allocated at the end of an object. Not hard to figure out. Not hard to figure out why they changed it. Yeah, indeed. But then again, with a B string, isn't it normally harder to actually control the bytes at the end instead of the bytes at the beginning? Not hard to figure out why they ended up changing it. Why did they change it? Because I thought with browsers and B strings it was easier to control the beginning of an allocation, harder to control the end. Was it because if you ended up overflowing a property? Yeah, there it is. If you overflow a property of the object, right, then you can smash the VF table. Yeah. Cool. Very cool. Yeah, that would have made some exploit devs a bit sad when they moved it then. That's Right on. Right on. In which case you need to be able to find an overflow in an object that you can make sure got allocated before the object and then go and smash it. Next, or if you haven't figured out, if no one's figured out, by the way, there's 15 seconds of delay between what I say and when you see it. So if we seem a bit out of sync in chat, it's because we've got 15 seconds between us. Alright, so that's what a UAF is. Let's go play with this binary and see if we can trigger one. So we were playing last time with set and show. So if we set foo to bar and then do show, we can see that foo is set to bar. If we set fizz to buzz, do a show, we can see that foo is set to bar, fizz is set to buzz. Now, because we can probably have heaps of these, get it? It's a pun about memory, heaps of them. If we can have heaps of these possible things being set by the program. I mean, we don't know if there's a limit. We don't know if you can only have maximum of 5 or 10 or 20. But it stands to reason that if we can have a bunch of them, then these might be heap allocations. And in fact, if we go and have a look at the set function, we can see that there's a test being done, branches, and on this side of the branch it complains. So this one here is probably where it actually does the setting of the thing that we asked it to set. So if we zoom in on this function here, stirdup is another one. Stirdup is also a heap allocator. Man, stirdup. Stirdup will duplicate a string. So stirdup looks like this. Constant char star pointer called s. Stirdup will return a pointer to a new string, which is a duplicate of the string s. Memory for the new string is obtained with malloc. So it's not another interface to malloc, it actually wraps malloc. And then the pointer you get back from stirdup can be freed with free. So if you're in a function and you want to basically create a copy of a local variable that you can then return to a parent or use in some linked list or something somewhere, then you can stirdup a string, which is basically just a nice wrap around malloc. It'll probably just do the malloc and then do like a stern copy or something of the sorts. So stirdup, if we ever see stirdup, then we know that it is basically a malloc. Do I use valgrind to look for UAF points? Just like the fuzzing, I'm not that good at my tools and my fuzzer tools and my valgrind, asan, all those kind of things. I prefer to do stuff manually because I don't know how to use the tools, but it also gives me the opportunity to improve my knowledge of the fundamentals of the issues. But it's definitely on my list to know how to use stuff like fuzzers, like AFL. It's on my list to know how to use stuff like valgrind, address sanitizer. I think msan is another one. I think there's asan and msan. Yeah, so we've got msan, asan, tsan, a whole bunch of other things. I think they're from Google that can detect memory corruption bugs at runtime, I think, based on spotting when there's a read out of bounds or a write out of bounds, or use after freeze. There's a really good way of detecting use after freeze under Windows. What you need to do is you need to use the Windows debugging tools, and you need to use gflags.exe to turn on page heap. And what turning on page heap will do is something probably similar to using valgrind to look for UAF. It'll make sure that when something is freed, the memory gets marked as not readable, not writable, not executable, and it never gets allocated again. So it's a memory leak by design. The longer you run the program, the more memory constrained it'll get, is because basically as anything in the heap gets used, then freed, that memory gets blacklisted, never to be used again. And that's good, because then when the program accidentally uses some freed data, it'll crash, as opposed to maybe happening to continue to keep on working, hiding the bug. So if you're doing use after freeze on Windows, make sure you understand how page heap works, because it may make the bug a lot more obvious and easier to debug. Yeah, it makes sense, doesn't it? An intro fuzzing series of streamings would be on spot. Yeah, I'll have to see if we can hook that up next year, because that does sound good. It'll be a lot of me failing and figuring shit out as I go, which seems to resonate with people. So people like it when I screw stuff up. So we'll definitely make that happen. So now that stirdup is a heap, it wraps malloc. So we can see that in this function that sets stuff, well, actually the function that gets called by the function that sets stuff, we can see a stirdup, which is indicative of the heap being used. And we've got a free here, got another stirdup here. We've got a calloc, which we know allocates zeroed out memory, and it's also got a different interface. It doesn't take the number of bytes, it takes the number of members multiplied by the size of those members. You can see there's a calloc going on here, more stirdup, some more frees in a different branch, another free down here. So we can see that the setting function is, well, the function called by the setting function is just running rife with heap allocations. So this feels good to me for the use after free. If we go to the show stuff, because the other thing is as well, by the way, we did figure out that if you go ahead and set fizz, it'll actually delete that variable. So that there's probably causing a free. If we set fizz to buzz1, do a show, and then set fizz to buzz 222 and do a show, that there's probably also causing either I didn't see any reallocs in there because this string has grown in size, probably caused a free then an alloc. So there's a lot of different ways in which we could potentially trip up the implementation that stores these set variables. So I'm just going to have a quick browse through the show functionality while I punch some sneaky clouds. Oh, the wind's picking up. Okay, so I didn't see the show functionality doing any mallocs or frees. So maybe we'll focus on set for now. Cool, I'm going to take a quick 2-minute break. If you need to grab a glass of water or a adult beverage of your choice, now would be a good time to do it. Let's reconvene in a couple of minutes and see if we can find this bug, trigger it, and see what happens. Catch you on the other side. Hey, and we're back. Yeah, Metasploitable 3, hey, that was on my list to have a look at over Christmas. Let me know if it's any good, guys, or peeps. And let me know if you think it'd be better if I save it for a stream. If you think it's streamable material, let's look at streaming Metasploit 3 in the new year, hey? Let me know if you'd be down for that. So, now that we know what a UAF is, let's see if we can play around with the setting and the showing and see if I can remember how I triggered the weird stuff last time. So if we set AAAA to BBBB and do a show, we can see it there. If we now set AAAA, there's nothing set anymore. Now if we set it again, do a show, we can see we've got one thing set. If we set CCCC to DDDD, if you weren't tipped off that there was a UAF bug in this binary, what stuff would get you going down the path looking for one? Old mate, you should check out the previous stream because I did beat up on it for a little bit. Can I hack NASA for you? Nope. Nope. Then, yeah, check out the previous stream, because I was going down that path till Mongo kind of steered me towards a different bug, which I'm so grateful he did, because that was a really cool bug to play with, find, and exploit. Then, yeah, go and check like the first half of that while I was wandering blindly, because I reckon I was about 5 minutes from triggering what I'm about to trigger, which I think is how I did it, following on from finding out that there was definitely a UAF bug there. But anyway, you're about to see the kind of stuff that I do, that I was on my way towards doing last time. So if we set a whole bunch of C's to a whole bunch of D's and show, cool. If we unset those C's, show, alright, cool. So let's put those C's back. What if we go and unset the A's and do a show? Okay, we can see some C's. What if we set some E's to F's, show? We can see that the E's got put in instead of the A's, because the order of it's now a bit mucked up. So that's interesting. I think that first spot might behave a bit differently because it's the head of a list. So we should dive into that. But let's go and add some G's to H's. Show. Okay, we've got the G's and the H's. Now let's get rid of this one and cause that variable there to be destroyed. So if we clear the C's and do a show, okay, we've got the E's and the F's and the G's and the H's, I's to J's, show. Hey, that's interesting. That's really interesting. Looks like we've broken it a little bit here. We had E, F, G, H. Then we put the I's in as J's, and that looks to have taken the spot of the G's and the H's. So that's interesting. We've got to find the right order to do stuff in to induce various kinds of corruption of the state of the set variables, and we can then go from there. So we've got the I's being J's. Let's set some K's to L's. Show. Okay. What if we get rid of these I's? Show. Okay. Let's set L, M to N. Show. Yeah, we've got some weird stuff going on here. We keep on losing things. Let's go and get rid of the E's. Show. We've got some M's. Let's get rid of the M's. Show. Let's go back to the beginning. A, B. Set the C's to the D's. Right, this is what I saw the other time as well. We're stuck in an infinite loop now. What do we do to get here? Scrolling up, scrolling up, scrolling up. Scroll. Man, it really ran away on us, didn't it? Yeah, that we're not going to scroll back fast enough. Let's look for dollar. There we go. Okay, cool. So what do we do? I think we're pretty deep down the rabbit hole now, but we got to the stage where we had A's being B's, then we added some C's being D's, and we did a show, and we got stuck in a loop where it looks like the linked list got broken and the last element was basically pointing back at itself, causing us to see this here. This looks really weird. So that's progress. Let's see if we can get to that state quickly. Let's see if we can get a minimal reproducer for this infinite loop, and then once we've got that, we might dive in and see how the heap allocators are working and seeing what's getting done in what order to give us this state. So we'll make the A's be B's. Show. Get rid of those. You know, let's set C's to D's. Show. Alright, let's get rid of the A's. Show. Get rid of the C's. Show. Alright. Let's set A's to B's. Get rid of it. Set the A's to B's. Set the C's to D's. Show. Alright, let's start again. I've got a feeling as to how it's happening. Let's set the A's to B's. C's to D's. Get rid of the A's. Get rid of the C's. Set the A's to B's. Set the C's to D's. Do a show. There we go. Okay, cool. We have to add. So what I did there was add two things. Remove the first. Remove the second. Add two things. And then we do a show, and that will infinite loop on the second element. So that's weird. That might be indicative of something funny going on. We should dig into it and see why that infinite loop's happening. Lots of tables indeed, and frames. Don't forget the frames infinite. Ah, Infinite, you're making me blush. So damn charismatic. Oh, I'll have to do one of those inspirational posters with that on it, so I can see it each day. And if you want to ban Facebook, you should look into their bug bounty then. Immanubes. If you want to burn Facebook, then you can get paid by them to do it. If you just want to see the world burn, then cool. But we don't condone breaking into other people's computers here. If you want to break software and build exploits, that's cool. If you want to actually muck with other people's machines, that's not okay. That's illegal in many places in the world. So let's test out this theory. We add two things, remove the first, remove the second, add two things, do a show. We should get an infinite loop. So let's set A to B, set C to D, get rid of the first one, get rid of the second one, set A to B, set C to D, and show. So we added two things here. We removed the first and removed the second in that order here. We added two things here, and then we do a show. And we get an infinite loop. Yep, infinite loop. Let's try this. Let's make a copy of this here. Let's swap these two things around. So we add two things. Let's remove the second, then remove the first. And see if that causes anything. I hate real people and love virtual people. And are you right? No. No. The reason I fall that way with exploits versus being operational is because I think that's where many of the laws differentiate. So you maybe, if you're an exploit engineer, if you're finding bugs in software and punching out exploits, or writing advisories and either sending them off to brokers and trying to get paid, or if you're sending them off to the vendor to try and get stuff fixed, or if you're just camping on it because you love camping on your bugs, you may get stitched up under reverse engineering laws, DMCA, terms of service use of software. Keeping in mind I'm saying software, things like a browser, as opposed to things like Facebook. If you're doing browser bugs and browser exploits, then you haven't really broken any laws. People may have their own opinions as to whether it's ethical or not, but at least you're not really breaking laws unless you go and sell to people on embargo lists. But as soon as you start chucking unauthorized traffic at Facebook, that can come under the Computer Fraud and Abuse Act kind of laws, where you're actually accessing systems without authorization. So, I reckon if you're accessing your own computer and the software on it in weird ways, it's your system. You can give your own consent to that action. If you're accessing the software running on Facebook servers in weird ways, they haven't authorized you to do it, you're probably breaking the law. So, an old mate. The other thing is, DMCA has certain provisions. You're allowed to break DMCA for certain reasons. And one of the reasons is for interoperability. I believe, I'm not a lawyer, don't quote me on this, and don't quote me in court on this, but I understand that perhaps one of the DMCA provisions is for software compatibility. If you want to make your software compatible with some copyright, digital rights managed, enforced bit of software, you can do it. So your defense can just be, I was making the vendor's software compatible. I was making my exploit compatible with the vendor's software, which might be an interesting defense under DMCA. What else am I using? The details are all down in the description below. All the bits of software I use. The TLDR is Debian Linux. This here is IRC client. This here is Tmux. This is a Docker container. Chromium. This is a Windows VM. This is IDA. And my streaming software is OBS. And this up here is i3, if I left that out. So there's the i3 window manager, the Tmux terminal multiplexer, Docker, IDA, OBS, IRC. Yes, Debian. Otherwise, check the description with more details below. All right, let's try this second case. So hopefully that makes sense. That's why I think it's okay. It's not that I hate real people and love virtual people. It's because I think that unauthorized access is a crime, and doing criminal stuff can be career limiting. And it can also be freedoms limiting if you get chucked in jail. No one wants to go to jail. Let's try this second one here. Add two things. Let's go and set... and that's all my opinion, by the way. Not legal advice, not ethical advice. Make your own decisions on what you want to get up to. So I'm going to add two things. Remove the second. So get rid of the second one. Then get rid of the first one. Then add two more things. Set A to B, set C to D, and show. That didn't infinite loop. So... I think the key is that we have to remove the first thing first and the second thing second to induce this type of corrupted state. And the reason for that is that if we have a look at the show function, func show, there's a function here being called. Yeah, I think I labeled this offset last time we were looking at this. We move that to EBX. We move what's at EBX into EAX. Then we check if it's null and do some stuff. We do a stir comp. against what's at EAX. Okay, cool. I think this here in .bss is a pointer to the head of the list of the items that have been set. So let's go and pinch that address there. Let's go and restart the process. Now if we break in GDB and do a telly at that for one location, telly you get for free with PETA. It's short for telescope. It shows you stuff in memory in a really nice way that actually shows you pointers being dereferenced. So this is PETA telling us that at this address the value 0 is currently stored. So if we continue, and if we go and set A to B, and we break again and do the telly again, we can see that at this location in memory we've got the pointer to the string capital A, which is the left hand side of this here. So at this address in memory, which I have called in IDA global vars, it's probably a bad choice in hindsight. It's probably a pointer to a head of a list sort of thing. We see this address here being stored at that location in memory, and then that address, if we go and copy that there, whoops, copy that, if we examine one string at that location, the string contains capital A. If we go and telly this location, then we can see that at the beginning of it there is the string capital A, and then some other stuff, and then the string capital B, and then some other stuff. So this here might just be uninitialized memory, maybe. Maybe we can have a name of up to 16 characters in length, or maybe 15 characters in length with the null byte. We should check the maximum length of this set of A, or this string here, and then we get the string B, and probably just some other uninitialized heap data. I'm pretty sure this is on the heap. If we do a VM map and we have a look at the layout of memory, then we're looking at OX9C3C054, and we can see at 9C3C000 through to 9C5D000, we've got the heap. It's a heap belonging to shitsco. And housemates are home, or there's a murderer in the house. I'm going to close the door so we don't pick up on their conversation. 1 second. Alright, so yeah, at this location in memory, which I've called global vars, this address here, we have a pointer into the heap, and on the heap we've got this here. We can see our A, we can see our B. Cool. And I reckon the first thing that we ever set as a variable kind of gets stored here as the head of the list. Then probably somewhere in all of this here, there's probably a pointer to the next thing, which doesn't exist yet. We should put something there. But the head of the list is special. It's a special case. It gets stored, a pointer to it gets stored in .bss as a global variable. So I reckon when you go and delete that one first, then the program has to go and mend the list itself, and there may be a bug in the way that it mends that list. And if you remove this one, then the other one, then go and put stuff back in, you can induce an infinite loop in the printing of stuff. I reckon that's why this one's important, because the first one gets actually stored in .bs, or the pointer to it gets stored in .bss. Let's start again. I'm curious. If we set let's make the variable name be 16 characters long. Let's set it to BBBB, and we'll do 16 characters of BBBB. Show. We get this back. How long are these A's? Python, length of those A's. Okay, we've actually got 16 A's. How long are the B's? Okay, it's 16 B's. Now if we break here, and if we telly that pointer again, telly that for 1, then we get a pointer to 8cc2, which is hopefully still the heap. Oop, VM map. Okay, so the heap is at 8cc2, cool. If we go and telly this, then we get 16 A's, FFFFFF00, OX19, a whole bunch of B's. Now, is this a heap allocation here? Or is that a second heap allocation? Because that could be heap metadata. I'm going to try 32 A's, see what happens. And 32 B's. Show. Let's go and get the length of this here to see if that worked. Python. Length of the A's is, yep, 32. And the B's, did we get all 32 of them? Yeah, we did. Okay. Let's go and break and do the telly again. And let's telly this address here. Let's go and get 32 things. Alright, so we got all these A's. And we got a 0. It's probably rounded up the string length to... It's probably rounded up the allocation size to the nearest multiple of 4 bytes. And then we've got OX29. That could be heap metadata. That may just be data from this chunk here. Looks to be a doubly linked list. Cool. Mongo, we got Mongo, do we? Mongo. Hey, Mongo! How's it go? Oh, no, that's not Mongo. That's Jardath. Mongo, how's it going? Good to have you around, dude. We're trying to dig in and see if there is indeed I'm told there is definitely a UAF in shitsco. We're slowly picking it apart and seeing if we can find something. We're just having a black box look at how the heap allocator seems to work for the setting of variables for now. What is OX29? 41. Okay. Yeah, I think it is. Size of the next chunk. I think it's the size of... I think that there... I think this is a heap allocation. With a trailing null. I shouldn't have done 32 Bs. I should have done 31 so that the null can fit in a 32-bit slot. Let me just do that real quick. Let's go and make it 31 A's. Get rid of one of them. B, 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 B. 1, 2, 3, 31 of the B's. Let's break and do the telly. And let's telly this for 64 slots of data. Oh no, we still get the null there as well, okay. Maybe it's not a null terminated, maybe it doesn't have to be a null terminated string. Maybe. No, it should probably still be. Smallest chunk you can allocate in 32 bits is 16, and 32 and 64 bytes. Yeah, cool, I'm chucking 31 A's, so that should be a 32 byte allocation, which should make that 16. Yeah, I'd love to, but I did start the stream. 2 a week is heaps indeed. At the beginning of the stream, I did say this will be the last one for the year. I do need to recharge the batteries over Christmas. If anything, I'll probably end up dropping to 1 a week. I do have a full-time job. I love streaming. It's a lot more tiring than you'd think. To talk for 3 or 4 hours on end and talk through what you're doing and talk through what you're thinking is just tiring. So I'm thinking I may eventually drop down to 1 a week. We'll see. I'm going to fine tune things in the new year and try some different stuff. More than twice a week is not going to happen. At least not while I've got a full-time job. It's too much. So I'd love to, but it's not going to happen. That'd just be, I would burn out doing that for sure. For sure. Why in movies do they have black screen and green font? It is annoying. It is very annoying. Love my solarized colors. 16 bytes and 32, 32 bytes and 64. Yeah, so I'm causing allocations of at least 31 bytes, so I'm not, less than a minimum, so that shouldn't be a problem. But yeah, that OX29 could be something with some status bits set, maybe. What's this plus OX28, maybe? Pointer to the next free chunk? Or sorry, an offset to the next free chunk, maybe? Ish. Offset to the next data. No. What's this plus OX28? 50B4. Okay, that could be this here could be the size of the whole allocation with a low bit set for previous chunk in use or something. I'm not totally up on heap metadata. We shouldn't need to worry too much about heap metadata tonight. We're not doing heap metadata corruption, we're doing a use after free. So this isn't actually too important. But this is probably 2 different allocations on the heap. Let's go and telly this again, not just 1 byte. Let's go and get some more stuff and see if anything jumps out at us. Okay, so we've got a pointer to the A's and a pointer to the B's. Cool. That makes more sense. That makes a lot more sense. Now let's continue. Let's go and set. Actually, let's stuff that. Too many A's. Set A to B. Set C to D. Break. And telly. Okay, so we've got... I think this here is... let's call this first var name. Let's call this first var val. Or a pointer to it at least. Then this here at 380 is going to be... Oh, nope. 380? No, what? Hang on, it's 36C. 36C. 370 is a pointer to the first var value. And then this pointer here is at 374. So there's another thing in here that's not being shown because I guess BSS, it's not actually being referenced at all. Hey Mongo, how do we create a new variable in BSS? Mongo is like our resident person who actually knows how to use IDA. I just fake it. How do I add a new variable here? Because it's got just a line OX10 here. I want to actually go and create a new variable. D key! Thank you, Mongo. D for Justin is derpy and doesn't know how to use his tools. Okay, so now we've actually got to set this to a DD. So it's, okay, so D was for data. Now I need to make this a DD with value and be able to name it. So it's not an array, it is data, it's just I've got to then N to name it. How do I, Mongo, how do I make this a DD width thing, not a whole bunch of bytes, but a pointer width? Ah, keep pressing D to change the size. Thank you, Mongo. Awesome. Okay, so it's a DD. So then we name it to be pointer to next variable. Next, second. Pointer to second to the second variable. Cool, because we've got this at that location we've got a pointer to something that points to CCCC. I've got a sneaky suspicion that if we go and add something else, let's go and telly this real quick. Yeah, so at this location we've got a pointer, no, a copy of CCCC and a copy of DDDD. Interesting. We've got a pointer back to the A's. Yeah, we've got a pointer back to BSS where the A was being pointed to. Oh no, this isn't actually it's a pointer to CCCC and a pointer to DDDD. That's okay, that's cool. Which we can see down here as well. Yeah, that's there. So if we continue, we go and set E to FFFF, break. If we just go and telly BSS, then we can see our pointer to A's, pointer to B's, and then our pointer to the pointer to C's. If we go and telly this, then we've got the pointer to C's, pointer to D's, a pointer to E's, and a pointer to A's. So yeah, doubly linked list. What we've got is we've got a doubly linked list. So BSS actually let's go and telly BSS again. Okay, so this here, they're not discrete pointers. I reckon this here is a struct. Yeah, I reckon this here is actually a struct. Which I need to totally learn how to do in IDA sometime. I don't want to harangue Mongo and get him to walk me through how to do that, but I should learn how to actually wrangle structs. Yeah, nice work, Nico. Nice work. Look like a total loser. He's talking to me, Okamidin. That's hurtful. Why are you like that? Why? I reckon this here is actually a struct where the forward link is set and the back link is set to null. And if we then go and look at the next record, then we get the 2 pointers to the name of the variable and the value of the variable. Then we get the forward link to the next thing, which are the E's, which is, sorry, the struct containing the pointer to E's and the pointer to F's. And then we get a backlink back to the A's. And if we go and telly the record that holds data about the E's, then we get the pointer to the E's, the pointer to the F's. The forward link is set to null because it's the end of the list, and the backlink is set to the pointer to the C's. So what we get is a doubly linked list. Double E. So BSS contains, so the struct record looks kind of like this. I don't know if this is valid C, but we're going with it. Actually, you know what? Let's make this a inline string. So we've got a char star var name. We've got char star var value. And then we've got a record star forward link, F link, and a record star backlink. So we've got these everywhere. We've got one of these in BSS. When we start the program, it probably starts off full of 0. So let's test that. Let's go and telly BSS. Yep, a bunch of 0. If we continue and we set AAAA to BBBB, then we get one of these put in BSS. We've got a char star, the variable name, which is a pointer to the string AAAA, being the name of the variable. Then we've got a char star, a pointer to the variable value, which is a pointer to the string BBBB. These are both stored on the heap. We've got a record star, forward link, 0, there's no next record, and a backlink is 0, there's no previous record, it's the one and only record in the list. We go and set BBBB to CCC, no, then we go CCCC to DDDD, break again. Then in BSS, we've got, again, the char star, the record star, forward link. The record star backlink is always going to be 0 for the one in BSS because you can't have a previous one. Maybe as we mess with stuff that we might actually see that light up, maybe. But we've got a forward link pointing to the record for the C's, which has also got its own pointer to the variable name, pointer to the variable value, a forward link, which is 0 because it's the end of the list, and a backlink, which points back to BSS, which has some data about the A's. So I reckon it's a whole bunch of structs that are doubly linked. I'm going to take a quick 2-minute break. I'm going to get some more water. If you need a break, now's the time, and we'll be back in a very short amount of time to keep on hacking. Back in one. I'll see you on the other side. So let's now that we kind of have an idea of how the application is maintaining the whole state of variables using a doubly linked list, let's I clicked something I shouldn't have. Let's replay this here, and at each stage, let's go and check out what the doubly linked list looks like in memory to see if we can spot anything weird going on. Actually, I probably should have just kept on going from where I was. So add two things. We've done this before. We've seen how the linked list works with that. So we'll set A to B, a bunch of C's to a bunch of D's. Actually, you know what? Let's for good measure go on telly BSS. And we can see that we've got the char star, the record star forward link, and the back link is 0. And if we go and have a look at this one here, the record with the C's, we can see a char star, forward link is 0 because it's the end of the list, and the back link goes back to the record over in BSS. Continue. So now what do we do? We remove the first. So let's get rid of the A's. Get rid of the A's. We'll break in the debugger. We'll have a look at BSS first. In BSS, we can see that we've got the char star and the char star are both set to the null pointer. The forward link is still intact, pointing to the C's, and the back link is 0 because there's no previous thing in the list. If we go and telly the record for the C's, looks pretty straightforward. Yes, it looks straightforward. We've got the char star, the forward link is set to 0, and the back link is set to 0. So the head of the list has no data in the char stars, but it does have a forward link. And the next record has no forward link or back link. That actually looks a little bit strange for a doubly linked list. Because, yeah, sure, you can go and null the strings out to kind of say this is a null record, but I would have thought that this backlink should still be intact for the second record. If my understanding of doubly linked lists is wrong, if that backlink being 0 is not surprising, let me know, but to me that's a little bit weird. So we can go and continue. Now we need to remove the second element. So we go and nuke the C's, we break in the debugger, let's look at BSS. We've got null pointer for the two char stars. We've got a forward link and no back link. So let's go and telly this for 4. And we've got no char stars, no forward link, and no back link. Now, okay, so the fact that the one in BSS has a forward link to this totally nulled out struct makes me think that maybe this struct has been freed, but here is the handle to it. We've still got a reference to it. My gut says that this might be the free. What we should do is set up GDB to log all the mallocs and all the frees. So to do this, I was playing with it the other day because I thought I'd have to do it tonight and I wanted to not look totally silly on stream. Let's go and do GDB cmd.append. Let's do a multi-line string. So when we start GDB, we want to, let's just start off with break malloc. So we quit peta. So if we do the exploit, I would have thought malloc would break by now. Oh well, let's go and set A to B, and there we go. That's weird. I really would have thought malloc would be called before we did it. Must have been no mallocing going on, I guess. So malloc gets broken on, and we have the opportunity to do things like check what just got pushed to the stack. We can see that OXC is the argument to malloc, so we're asking malloc to give us OXC bytes worth of space, which is 12 bytes, which is weird number. So now, it's going to kind of suck if we need to go continue, and kind of look at all this up here to kind of get more information as we go. So what we should do is we can actually, with this breakpoint on malloc, we can set commands. And we can tell GDB to print OX1337, continue, and then we type in end to end the commands. And so these commands will be run every time malloc gets hit. So we go and do that. We go and set AAAA to BBBB. We can see that for each of the mallocs, we saw that the breakpoint got hit and OX1337 got printed each time. So that's kind of cool. This gives us a skeleton upon which we can start to hang some useful print statements to actually tell us what's going on. So what we'll do is for debugging, we'll get rid of this continue for now. I think you can just hash stuff out in GDB, can't you? Print 1, yep, hash print 1. Yeah, cool, so GDB can have comments and scripts. So we'll just hash that, we'll comment that out for now. We need to think about what sort of stuff we should run upon each breakpoint to hitting malloc. Let's go and set AAAA to BBBB. Cool. Something we should probably do is print out a stack trace. Should we do 2 deep? We should probably do 3 deep. 4 deep. Let's as soon as this malloc breakpoint gets hit, let's get a 4-frame deep backtrace so we can kind of see from where the malloc was hit in case we need to kind of walk back up the stack and see where we got to that malloc from. What else do we want to do? Let's get the context. We need to print out, at the beginning of malloc, we need to print out this value here because it's how many bytes we were asking for. So to do that, we can go printf malloc something, new line, and we need to just replace this something with ox%x. Ox deadbeef. Yeah, cool. So now if we can find a way to resolve this value here off the stack, which is the function parameter for the malloc, we can kind of put it here, and then the printf statement will show us what's happening. So how are we going to go and fish this value off the stack? Well, what we can do is we can go and print $ESP, which we know should be FF9F697C. There it is. We could do $ESP -4 +4 down the stack. Yep. And if we go and print out the malloc of $ESP +4, we should see malloc of this address here, 6980. Cool. So we're getting somewhere. Now what we need to do is we need to actually go and fish out the integer, or the malloc takes a size t, I think. Yeah, malloc takes a size t, but I couldn't find a way to actually cast stuff to a size t in GDB. Maybe someone else can school me on that. We need to go and chuck a star in front of the $ESP +4 to say, go and dereference it as a pointer and get us what is at the address, $ESP +4. And GDB will complain that we're trying to deref a generic pointer. So if we just go and cast $ESP +4 to a size t star, it'll complain because it doesn't know what a size t is. What if we just make it a void pointer? Nope, unhappy about that. Pointer to an integer. That'll do. Integer is not a size t, but I don't know how to get GDB to cast stuff to a size t because I'm silly. But now we can print out the size of the thing. If we don't like it in hexadecimal, we can just make it a %d and get 12 bytes. Let's be real computer scientists and actually get hexadecimal. So now what we can do is drop this here in our GDB script. Oop. It's not what I wanted at all. We need to escape this backslash. And every time malloc gets called, we get rid of this continue, the comment in front of continue. Every time malloc gets called now, if we go and do a set a to b, we actually get log info. You know, here's we hit a breakpoint. Here's the stack trace, and we can see that we called malloc oxc, and then we called malloc with a whole bunch of ox5 requests. I'd rather see this call malloc. Yeah, no, I'd like to see it after the stack trace actually. Yeah, let's go after the stack trace. We can see that the breakpoint was hit in malloc, which makes this kind of redundant, but I don't know, I like seeing that we mallocked ox5. That's kind of cool. Now, we also want to get the return value of malloc. So what we should do is get rid of this continue and do everything again. Set a to b. Cool, breakpoint got hit in malloc. And we printed out our call malloc oxc stuff, having fished the parameter off the stack. Now we want to finish this function and get what is in EAX at the time of the return of malloc, because we know that on x86, return values of functions are provided to the caller via the EAX register in most cases, unless it's a big thing that it needs to return, in which case magic happens, but that's not the case here. So it'd be kind of nice to see what address malloc returned, so that we can then kind of maybe double check. And when we do our tellies later and see something that's getting used after a free, we can kind of scroll up and see from which malloc it came. But we need to find out what EAX is at the time that malloc finishes. And from what I was googling, the way to do this is to go up a stack frame, break on the next instruction, and continue. And this should get us to the instruction following the return from malloc. So if we continue from here, then here's our called malloc, and we can see that in EAX, here's the pointer. Here's what malloc, here's what this here is what this call to malloc ended up returning. So this here is a allocation of size oxc. So that's kind of cool. So if we again go, we'll put the continue back in, but before the continue, we want to go up, break on the next instruction. The commands for this breakpoint, commands need to be print returned %p. We want to print it as a pointer. New line. We just want to get what's in EAX. Easy. $EAX. And these here are the commands for this breakpoint, which is the breakpoint on the next instruction after this malloc was called. So after that's been done, we want to continue and then end these commands. And so keep in mind that these kind of stick together. This breakpoint is having these commands attributed, and this breakpoint is on the next instruction after we go up from where the context from which this breakpoint fired. So we go up one, we finish these commands here off. We want to continue after this breakpoint and then end these commands. Hopefully that makes sense. Where did I pinch this from? GDB debug malloc. I should give credit where credit is due. Who did I steal these from? Log malloc free. Here, this gist, AOSEC. Yeah, I stole them from here. But I kind of wanted to step through the building of them bit by bit as I understand them. I think that'd be more useful than just copy pasting this here. So credit where credit is due. Thank you AOSEC for this little snippet. It helped me get my head around how to set up the logging of mallocs and frees. So now this is all set up. We save the script, we quit, we do the exploit again. Now if we go and set a to b, what do we get? Not what I expected. Where's my return values? Where's my return values? Print F, not print. Let's change this print to actually be print F. Let's try that again. Run that. Do the set A to B. Cool. So if we scroll up here, actually these stack traces are kind of annoying me. I might turn them off just in the interest of saving space. If we need them, we can turn them back on. But we can see that we called malloc with the argument OXC. In fact, I should turn this here off if I can. And this malloc here returned that value. This malloc OX5 returned that value. That's a weird looking return value compared to that. Actually, that's not a return value. That's a return value. They look fine. I'm going to see if I can clean up this output a bit. It's a bit distracting, as evidenced by the fact that I just stuffed something up. So where does this... the keyword silent needs to go somewhere. Okay, command silent. That should shut up some of the built-in stuff. Let's silence that one. Silence that one. Let's get rid of this backtrace. I don't know if we're going to need that just yet. Try that again. Set A to B. That's a bit better. So we can see that malloc OXC returned this. After this returned, I probably want an extra new line. So we'll chuck that new line here. Try again. That's looking good. You can see that a malloc of OXC returned this, a malloc of OX5 returned that, a malloc of OX5 returned that. All these OX5s are probably based on the string length of A plus a null byte, B plus a null byte. In fact, we should test that. Quit. Let's go and set A to B. So the A is 5 bytes long, the B is 6 bytes long, and what do we get? We got a malloc of 6, probably for the A's, malloc of 7, probably for the B's, a malloc of 6, probably for the A's, and a malloc of 7, probably for the B's. And we got different addresses each time. So now if we break this here, whoop, lost all my... Let's, I reckon this allocation here probably had the A's written to it. So if we examine one string at that address, empty string. Maybe it was just a temporary thing. I reckon this malloc of 6 got the A's. Let's go and spike this string here. Hey, we got the A's. Oh yeah, because this is the stirdup. Yeah, right. So these mallocs here are from the stirdup. These mallocs here are also from the stirdup, but I reckon they were probably temporary ones. They were probably freed at the end of stirdup. We need to set up logging for the freeze as well, so we can get an idea of what's being allocked and what's getting freed. I reckon this malloc OX7, which returned this pointer, probably holds our B's. Yep. So this is the stirdup A's, this is the stirdup B's. And then if we go and tally what is on BSS, yep, our pointer to A's, which was strduped, is in the first record or the first element of the struct. The pointer to the B's, which came back from stirdup, calling malloc, is the next element of the struct. So this is starting to actually make sense. It's how we'd expect the heap allocations for the first thing, the first variable having been set, triggered some stirdups, and the pointers to the duplicated strings. We know that strduped duplicated strings are allocated on the heap, and stirdup duplicates the strings and puts the copy on the heap for us. And we know that then the pointers that came back from the malloc, which was done by the stirdup, got put in the record, the struct record in BSS. This is actually not that surprising. This is making sense, which is always good when you're dealing with the heap and stuff makes sense. You're having a good day. And this is not crazy heap stuff either. This is just like basic use of the heap. But the heap is a cruel mistress with many special attributes. So any day that you can say this use of the heap makes sense should be a good day for you. Alright, let's do the same for freeze. So we want to be able to set a breakpoint on free, break free, and run the commands. Silent, printf, call free with an argument of ox, %x. I'm just, if you're not realizing, copying verbatim from up here. New line, escape the backslash. Same thing for free. We know that we're getting a pointer as the first argument, or as the only argument to the free, so we're going to pull that off the stack. I wonder if anyone's yelling at me for this int star, because that's probably really bad form. Steel, inspired by, same diff, right? Jardeth, good to have you around. Yep, catch a new year indeed. It's been a pleasure hacking with you, Jardeth, this year, and I will be looking forward to the next one. Sleep tight. Yes, you can. You can indeed, but I'm not gonna go down that rabbit hole just tonight if I don't have to. Wouldn't rely too much on the size parameter you're reading, because malloc will then need to set the size and alignment boundaries regardless of the parameter. Yeah, cool. All I want is a bit of context to be able to say, oh, it's a malloc of about the size of the struct. It kind of just lets me mentally kind of go, I think I know what this allocation is going to be used for. It's just a bit of a hint that can help me make silly assumptions and end up hacking till 1 o'clock in the morning based on bad assumptions. It's just a bit of context, but good point. Yeah. You're right, the size and the alignment boundaries, malloc has to round stuff up, malloc adds its own metadata. Luckily tonight we're not doing heap metadata corruption anyway. It should just be a pretty standard use after free in kind of the application sense of the use after free. So you're right, malloc will cause roundings and alignment, but that's not really what we're too worried about tonight anyway. We kind of also want to know what the size is so that we can make sure our replacement alloc fits the right sized freed thing. Okay, cool. No one's yelling at me for this star int star stuff, so I'm going to keep on doing it, even though it's probably terrible computer sciencing. So we're calling free. Actually, we don't need to do this anymore. We know it's going to be a pointer. We'll go %p and get this star int star at ESP +4 to go and fish that pointer off the stack. We don't care what free returns. We don't need to do this upbreak command stuff. Continue and... because does free even return anything? What does free return? The free function returns no value. Yep, free is a function of type void, whereas malloc is a function of type void star, so we do care about what it returns. Free doesn't return anything. At least nothing interesting. So we don't need to go and do this nonsense. We can just accept that the free got done. Let's try out the new addition to our logging stuff. So if we set A to B. Right, what do we get? Okay, so we got a malloc of OXC. It returned this address. It ended up getting freed by the time we got control back anyway. Then there was a malloc in stirdup of 018, which got freed. There was a malloc within stirdup of 028, which got freed. So all that really stuck around after adding AAAA and equals BBBB to the list of save parameters, these 3 pointers got freed. We were left with these two stirdups sticking around, which is where the AAAA and the BBBB are. They were stirduped duplicated strings, and then the pointers that came back from these mallocs were saved in BSS within that record of the set variable. That makes sense. Again, when you can say that makes sense, you're having a good day. Now let's set CCCC to DDDD. And what do we get? A very similar output, which is weird because we should have expected to see an allocation for that new struct that becomes part of the doubly linked list. The reason we didn't see that was because, if I recall correctly, that next element in the doubly linked list was not allocated with malloc. It was allocated with calloc, which we haven't set up logging for yet. So we go to the func set. I think we dive into this function here. I think I saw a call to calloc. So here's some of our stir dupes, some stir comps, and then here's our, that's a stir dupe. We've got a free, blah blah blah. Yeah, call to calloc. So if we want to be able to see this alloc, it's another memory pun, that one. If we want to see this alloc, then we need to set up logging on calls to calloc as well. I wonder if calloc mustn't wrap malloc, because otherwise we should have seen a call to malloc coming from calloc in this, and we didn't see one. So yeah, we need to set up logging on calloc, which should be pretty similar to the malloc one. Yank 13 down, paste that there, break calloc, and we get a call to calloc. Now calloc does take different parameters. Calloc takes two parameters, a size t for the number of members and a size t for the size of each member. So we need to go and rip two things off the stack. We've got an ox%x and an ox%x. We should be able to just go and yank to the comma, go and just pull two things off the stack just like that, for our logging of how the calloc was called. So we go and fish the first parameter off, gets put here, and the second parameter at +8 gets put here. The function parameters get pushed in reverse order. So this should be fine. I think that'll be fine. I'm going to leave out this continue anyway, so we can debug it if we need to. Then we're going to go up a stack frame, set a breakpoint, command silent, print out return from EAX. That should be fine. Cool. Let's go and just check this out real quick. So now if we set A to B, we get a whole bunch of, I was pointing at the screen, then you can't see what I'm pointing at. A whole bunch of login going on. Now if we set our CCCC to DDDD, then we see that our break to calloc actually didn't continue because I commented it out. Let's have a quick look. We've got a call to calloc, ox1, ox10. Parameters are here. First parameter is ox1, that looks good. Second parameter is ox10, that looks good. In fact, we should probably decorate calloc. It's nmemb and size. We should probably decorate everything actually. nmemb equals that. Size equals that. Mind you, we know what the argument to malloc is. We know what the argument to free is. We don't need to decorate those with descriptions. Let's get rid of this continue. I reckon we should be sweet with our calloc logging. So we set A to B, set CCCC to DDDD. Let's see what we got. Yeah, we got a malloc of OXC 5 and 5, which we see get freed down here. Yep, 008 gets freed. 018 and 028 both got freed as well. Then we see this call to calloc, with the number of members being 1, the size of the member being OX10, and we know that calloc is going to return zeroed out memory, and it returned this here, and then we've got a couple of stirred oops happening. I reckon this here, this is going to be a pointer, which was returned by calloc to the struct representing the second thing in the linked list of variables being set. So it should be the struct to do with ccccc equals dddd. Let's go have a look at that. Scroll back up, grab my calloc return, copy that. Let's tally 4 elements of that. Oop. That doesn't look right. What did I just do? Did I copy the wrong thing? I'm going to copy the return value of calloc. Yeah, I did copy it properly. That doesn't look right though. This should be a pointer to C's. It looks really weird. What have I done wrong here? And this is a backlink to what? Tally that for 4. Garbage. Continue, show. Interesting, we can see that a show causes a malloc of 8. I'll go back this and it freed it anyway. Why was my return from calloc not making sense? I'm gonna set AAAA to BBBB, set CCCC to DDDD. I'm gonna grab a copy of this here. Let's just chuck it here for safekeeping. Let's break. Let's tally BSS. Calloc, I would have thought would have returned this pointer here. D058, did it? Yes. What was I doing wrong? If I copy this return value of calloc, copy, oop, and then tally that for 4. Strange things abound. I was seeing nonsense before. Did someone see me doing something silly?
I'm running away from this pain. I'm trying to find a new way.
Cheeky. Yeah, I mean, if Malloc's under if your memory's if your memory's constrained, like if you're running out of memory, then malloc should start returning probably a null pointer when it fails. So that's why when you malloc stuff, you should always check to make sure it actually returns something other than 0 before you go and use it. It does sound like House of Force indeed. Yeah, shitsco is a CTF challenge Mongo. Mongo's bang on with that. What is this for programming language? Well, the program was probably written in C. We're looking at the disassembly of it in x86 assembly, and I'm writing Python. Actually, it's kind of confusing. What I'm doing is I'm writing Python for the most part, like this here, but I've got a whole bunch of GDB scripts interspersed with my Python just to make life interesting. And I'm currently kind of debugging the GDB script because I saw some weird stuff a second ago. AAA to BBBB, set CCCC to DDDD. So calloc returned this. Let's copy that, break, tally that for 4. I was seeing weird shit a second ago. I don't know what went wrong, but it's working now. I'll have to check the VOD later to see where I was going wrong there. Cool, so yeah, it's the logging of calloc worked. That's kind of cool. Now, let's continue with what we were doing before. We're really I'm taking the very slow, leisurely way leisurely way around actually solving this and trying to explain as we go. Let's go back to what we did before, where we added 2 things, then removed the first. Let's see if there's a free of something for which we can still see a pointer to in the doubly linked list. Because again, I reckon it was when we removed the first that there was still strangeness. Maybe. Let's try. Let's go and clear out that first allocation by blanking out the. Let's continue GTB. Let's blank out that first variable, the AAAA variable. And what did we get? We got a bunch of frees. I reckon the net effect is it freed our stir-duped strings for AAAA and BBBB. Just going to search up for that. Yeah, so these stir-dupes gave us back 6038 and 6048. So they got freed. So that's actually not that strange. If we go and telly BSS again, that's not what I wanted to see. That looks better. So yeah, these 2 pointers got set to null because the stir-dupe strings there were freed. That's fine. We've still got a pointer to the next element because that we didn't free that. That's fine. If we go and telly that for 4, we can see the pointer to C's, the pointer to D's, forward link and back link are both null. Okay. Let's go and remove the second thing and see what happens. Set CCCC to nothing to get rid of it. What do we get? We get some mallocs and some frees. Okay, so we can see that we mallocked some stuff and then we freed it here. We freed 3 pointers. 2 of them are going to be the strings CCCC DDDD, and one of them, which I reckon could be this one, was probably that struct. Nope, I was wrong. The struct was at 058, which got freed, and then the 2 strings at 70 and 80 also got freed. Now, is there still a pointer in BSS perhaps to 6058? Yes, there is. So, that memory has been freed, but there is still a pointer in existence pointing to it as part of the linked list. And it's currently full of what? Let's tally that for 4. It's full of nulls. Now, if we were to be able to cause an allocation of 16 bytes that looked vaguely like a struct, say filled it with A's, and then we did a show, this pointer here would get walked to this element in the doubly linked list. And we could put some nonsense data there. If we can find an alloc primitive to let us replace this with a 16-byte allocation, and we can control the data there, we can control an entire record. We can put a whole bunch of stuff there, and then do a show which will cause a couple of string pointers to be dereferenced, and the contents of what it points to return to us. That'll give us an info leak. We can probably also set the first one to a pointer to a string that we know, and the second one to some data in memory, and then try and change the variable named as per what we pointed this one to. We can probably get a write what where primitive out of this as well. if we can find a way to cause a 16-byte allocation to perfectly kind of snipe this spot and keep everything looking sane enough that we don't get crashes, this is our UAF. When you create two variable settings in the order that we did, destroy them in the order we did, there's a pointer in BSS that hangs around as a forward link to some freed memory. And if we can put some stuff there, we can then cause this to be used after it's been freed, and have our own dummy struct element in the doubly linked list be treated as a bona fide element in the linked list. And we should have some fun stuff to play with. Now we need to find a way of allocating 16 bytes and having it stick around in memory in a way that is also not going to destroy this pointer. How can we cause 16 bytes to be chucked on the heap and not wreck our shit here and cause it to... Well, actually, it doesn't need to stick around. It'd be nice if it sticks around because then it won't get overwritten with subsequent mallocs. Do we have a replacer primitive? So dispatchable malloc stuff. Is that malloc useful to us? Or will it get freed? So we had a malloc of 8, and then it was freed. I reckon we're going to need to use set again. As long as we set with correctly sized strings, maybe we can cause a 16-byte allocation to stick around. Let's try that. Let's go and set. If we show, we've got nothing so far. If we set a variable of the name being 15 A's, 1, 2, 3, 4. 1, 2, 3. Get rid of one. Because it'll probably want to null terminate it for us. B, 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 B. 1, 2, 3, 4. Get rid of one of those. What do we get? Do we have an allocation of 16 bytes that sticks around? That replaces... Actually, we should scroll up and see the address. We're looking to replace 6058 with a 16-byte allocation that sticks around. 6058. We did malloc at 6058, but then we freed it. I'm guessing 6058 is now empty string. Let's tally that for 4. Okay, no, we control it. We control the... that null pointer is probably going to kill us. We want to get an allocation that sticks around, that doesn't get freed and then nulled there and... Blech. But still, if we now show, we get a crash. We probably got, yeah, a read of for one. So I mean, this is triggering the UAF now in a way that's probably more useful than the infinite loop. But I'm still not happy with the control we had. Let's do it again. Let's go set A to B, set C to D, clear A, clear C, set 1, 2, 3, 4. How can I do this differently? Let me just think for a second. Nah, because the replacer is always going to get freed because malloc seems to make a temporary copy. By the way, this whole thing is predicated based on knowing how libc works. If you're attacking someone else's libc and maybe they've got a stirdup that doesn't make that temporary copy, your exploit would probably have to account for that if you're using stirdup as a replacer. Get rid of one of the A's. Let's go B, 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 B. Paste, paste, paste. Get rid of one of them. So we've got two 15-byte strings being sturduped. Let's break now. Let's telly BSS again. And now if we telly the next, what the F-link points to, then we get some garbage data. Yeah, but it's been freed, which sucks. Be really nice if that allocation could stick around. Maybe it doesn't really matter. Maybe it doesn't really matter. What do we want to use this for? Probably a write what where. I mean, let's do a check sec. Let's see what we're up against. ASLR is off, so we probably don't even need the info leak. Dep is on. So what we could do, I mean, keep in mind as well, there's already code in the program for printing the flag. Where is it? Where is our flag printing stuff? Crossrefs. Now, we could probably push sub. Where is the return from this here? Where does the flag printing start? I mean, we don't really need to know where it starts. We can just pick somewhere within it. Like we could use a write what where and spike the got, and we could probably write the address of the flag printing stuff straight to somewhere in the got and just trigger the flag printer. Let's go set up a flag real quick so we know we'll move one. Vim flag. Oh, I've already got a flag. Cool. Let's start with that, and then if we're feeling eager, we'll move on to seeing if we can shell it. Now, if we want to write what where, then we need to keep this pointer alive. Because the way I think we're going to use and turn this into a write what where, remember the struct looks like this. We've got a char star for the variable name. We've got a char star for the variable value. We've got a forward link and a backlink. The F-link and backlink we probably need to set to null, which is going to suck a lot. Bleh. Yeah, we need to make sure these F-links and B-links don't get walked in a way that crashes. Ugh. Yeah, we need to think of something we can put. Well, we can just set the forward link to a pointer that has a whole bunch of nulls. No, that's going to cause crash. we can set the forward length to a pointer at which there is a valid-ish looking struct that has a resolvable char star, a resolvable char star, then the forward link has to be null. And that should get us out of crash territory. Anyway, how I think I'm going to turn this into a write what where is by using the fact that you can reset the value of variables. And if we could have this persist as a pointer to a string, for example, probably just pick a string out of the strings window here, a nice short string like $3.2 or home shitsco password, and then later on come along and try to change the value of that entry, which will probably stir up the new value, and then yeah, we're gonna have to think about how to turn this into a write what where. Okay, we've triggered it. We're on the right track. I'm gonna take another quick 2-minute break and get some water, and we'll pick up there and see if we can turn this into something cool. So I'll see you on the other side of a quick break. Alright, as soon as I stepped away, I realized what we need to do. Shells will be cool. I think shells will be maybe stream number 3 if we want to stream this one again. What we really need to do is get to the flag function and execute the flag function. And there's 2 ways we could do that. We could use a write what where primitive to spike the got and set the pointer of some function that we know gets called a bunch, like the printf function, and make that point to the print the flag function. And then every time printf gets triggered, the flag will be shown. That's one way. The other way would simply be to spike the area in .bss, which holds the you are authenticated flag. Which, if we just zoom into the authenticate user function, there'll be an offset to... We could probably spike the enable password, but I'm thinking we should spike the... this here, this offset. User is authenticated. User is authed. If we go back, then the authentication function, if you know the correct password, moves the value 1 to this offset memory. which is an address in BSS, which is a DD value. Ida thinks probably is a DD value actually, which holds the user auth value. If we just go and print that right now, then we get, oops, 0. We're not authed. If we can spike that to make it 1, or probably just make it something that's not 0, we should be able to call the flag function and just get the flag. If we can use some sort of, not even a write what where primitive, but just a write primitive to damage BSS, we can safely, if we can damage this to become non-zero, we should be sweet. We just need to make sure there's no collateral damage that causes a crash by modifying. We don't want to probably, we could probably damage that. It's just data, I think. We want to make sure that this is not straddling. This should all be writable. Let's go and check the VM map. We're looking for C3, C0. Writable, and the heap. Yeah, so we should be fine to just go and damage that general area. What have I missed in chat? Thank you very much, CRZZO. Appreciate the kind words. Awesome. I'm glad you're enjoying it, OTZ. Thank you very much. If no one was around, you know what? I'd say I wouldn't be doing this, but I would. I love doing this kind of stuff. But the fact that people get something out of watching me stumble through it makes me very happy. So thank you very much for the kind words. I appreciate your company and your support very much. If we can just damage this user is authed and make it non-zero, I think we should then be able to do the print flag. Like, let's get the cross refs to user is authed. So it's being read here. It's being read in the dispatcher. We should probably check what the dispatcher is doing. It's reading it to EAX, comparing EAX with EBP. What's that? EBP plus 8. Making a decision. Brr. What's that? EBP plus 8. Please don't be comparing against exactly 1. What's that? EBP plus 8. What is that EBP plus 8? An argument to dispatcher? Where is dispatcher called from? Second argument of the function, yeah. You're a C# guy. That's cool, mad scientist. Yeah, this isn't totally relevant to C# kind of stuff. C# being like I think C#'s a pretty highly managed language, yeah. We're mostly dealing with pretty low stuff. Like, yeah, this would have been written in plain old C, and then compiled to machine code. So it doesn't necessarily mirror what you'd be doing in C# day to day. Hopefully you still get something out of it. I think it's still important, even when you do write in managed languages, to understand how computers work on a low level. I think there's a lot of benefits to it. And if you're a hacker, then knowing what happens on a low level is awesome. So yeah, is EBP plus 8 referring to an argument to dispatcher? Well, there is no explicit argument to dispatch. There's only one, which is the string. Being dispatched. Where was that offset? User is authed. Let's come back to dispatcher. Let's go to this use of it here, which is probably in the read the flag function. What's being done with the user is auth. Again, we're comparing it to EBX plus 8. What's that EBX plus 8? I don't reckon that was. I reckon EBP is being abused in dispatcher. I don't reckon it's a base pointer at all. So in this case, we're comparing after we get the user is auth. We're comparing against EBX plus 8. EBX is currently. How can we get to here? From here-ish. I reckon there's a table of available commands there. I reckon S2. What's at S2? What is it, S2? Is S2 like a table of different auth levels for different functions? I reckon it might be. Compare EDX against EBX plus 8, JG. Oh, I reckon, no, this here's the printing the menu. And yeah, it makes conditional. I don't really care if the menu gets printed properly for us or not. This is a spurious use of user is auth that I don't really care about. I don't care about whether it prints the menu for me properly or not. Where else is user is auth being used? In dispatcher. There's some direct compares. This here might be the flag one. Nope. But there is a comparison of 1. Do we need to set user is auth? We can probably just make this up. Let's make shit up. Let's quit this. Let's kill that. Let's run the exploit. So we can look at the menu. Let's just go and spike that value in GDB to be exactly 1 and see what happens. So how do we do this? Is it star int star at that address equals 1? Nope. How do we change memory with GDB? GDB set. Set something equals something. Now let's go and examine that is auth flag. And I set to 1. So now we continue. We get our nice little pound symbol and we go help. Whoops, we go question mark, then we go flag. And because we've got is auth set to 1, we can look at the flag. Let's break. Let's set it to 2. And see how the program behaves when we have an is auth value of 2. Continue. We still get the pound. Help says flag. We do flag and we get that. Let's go and set the is auth value to OX dead beef. And see what happens. We still got the pound. question mark is not a valid command. Flag is not a valid command. So we can't have isauth set to OX dead beef. Let's set it to negative. I'm curious. Let's set it to -1. Let's go and examine it now. Did that do what I think it did? Yeah, cool. So now we do question mark. No. Flag. No. Let's go and set it to int max. OX7 FF. Because maybe when we set it to OX dead beef as a signed integer, it's actually a negative number. Let's go and set our isauth to a really big positive number and continue. Help. Yep, cool. Flag. There we go, there's the flag. Now if we go and set isauth to int min, which is OX80000000, which is a really freaking big negative, like a really small negative number, and continue, then yeah, the menu breaks and flag breaks. Okay, so as long as we spike the isauth value to be 55555555, as long as it's a positive integer, then we can do the flag function and we win. So if we can use some sort of primitive with our useAfterFree to ensure that the isauth value gets spiked to become a positive number, we're home and hosed. And I reckon we can figure out a way to do this. If we think about how forward links and backlinks and these two char stars work, we should, even probably with the replacer being ephemeral, we should be able to sneak in some sort of spike of, is it .bss? Yeah, the user isauth value. I think we should be okay. How are we going to do this? What about our replacer? We can't control the variable name with our current replacer primitive, but we can control the forward link and the backlink, and we can control this char star. What are we going to do to get a right primitive that will just let us spike this value to something? Like if we set the f-link to point somewhere towards it, what will that give us? Yeah, if we set the forward link to point at the value, and then cause another allocation, as long as that new allocation doesn't then corrupt our list in a way that gets crashy, we may be able to get a stir loop and then a write of the stir loop to point it back from stir loop to var name, to the char star var name, which should let us spike it to something. Let's do that. I'm going to start actually putting stuff over here to make it more repeatable. Actually, you know what? I am, because I'm going to write pointers. Let's go t.send line, set a equals b, set c equals d, then we need to t.send line, set, we need to kill the first one, and then kill the second one, and that there, typos, that should get us to the corrupted state. Let's check. Break that. Let's telly BSS. Yes, this is the corrupted state. If we telly this, it should be a totally null record. Yep, cool. So now we're in the corrupted state. We now want to actually, yeah, let's t.send line. Actually, it's it's not a gets, it's a read, isn't it? We probably can read null bytes. We probably can read null bytes. Let's go t.sendLine. Let's try some null bytes. Let's go and send pwn.p32. Let's go and send a null pointer, and then oxdeadbeef. Let's see if that at least makes it into memory. Invalid command. Oh, we didn't need to send that. We needed to send set plus we wanted 15 bytes. Let's go and put the dead beef there and then just go BBB plus a space plus CCCC. So what this should do is, actually we should probably create a helper function to get some logging. Def set new var. I'm going to take two arguments, the var name and the var val. pwn.log.info. Setting new var of name. Let's go and put the length there just so we can kind of keep an eye on the lengths of name. That val a length and a value. I'm going to go to the len of var name, the len of var val, and var val. t.sendLine, set that to that, dot format, var name, var val. Probably could add error handling in here to not let it, yeah, let's, no, bugger it, I'm not going to do error handling. Now we're going to do set new var a b c d, which handles those two, and we need a new function for def delvar or rmvar. Var name, pwn.log.info, get rid of this space, deleting var of name, length, name. Oops, that's not what I wanted at all, that's a dot format. That's a dot format. Len var name. Oops, not what I wanted. So when we're RMing, we wanted pwn.log.info, deleting var of name, the length and the value, format length value, yep. t.sendLine, set that to nothing, var name. Cool. So we're going to rm the var a, I'm going to rm the var c. Handles those two. Let's just check to make sure those work. Yeah, there we go. Now we've got nice logging about exactly what we're doing when we're doing it. We're setting the var of name length 1a to the value of length 1b. cd, deleting var of name a, deleting var of name c. Cool. I like that. So now we've set up the corrupted state. t.log.info. Get to corrupt state. Now what are we going to do with it? We're just going to try setting a pointer with null bytes. We're going to try setting try allocking a replacer with nulls. I'm just curious if this is going to work. So we're going to set new var. Of this nasty string, which is going to be pwn.p32 plus pwn.p32 plus pwn.p32 ox deadbeef, which is going to be the forward link, plus bbb, some trailing bytes to take us out to the length we want. And the value can just be e, I don't really care. Get rid of all this nonsense. Let's see if we can get these nulls and that deadbeef in memory. And we get a, whoops. No, not t.log, pwn.log.info. That's what we want. And we got a crash. What did I do wrong this time? Function object has no attribute info. Did I not save properly? Oh, here it is. pwn.log.info. Cool. Derp, don't mind me. Alright, so yeah, we've tried to do our whole deadbeef trick with a name of length 15. Let's see if it worked. Let's break there. Let's go and telly BSS again. Oops, that's not BSS. There we go. Let's go and dump this. Telly that for 4. No, I don't think we can get nulls. I don't think we can get nulls. Fizzer. Oh well. Just to verify that, let's make these all deadbeef. OX deadbeef. OX deadbeef. Try again. Let's go and telly VSS. Yeah, there's our deadbeef. Oh. Hang on. Okay, yeah, there's our deadbeef there. And our deadbeefs here, and our BBB there. Cool, so the F-link currently points to a record with a char star of being null, a char star of deadbeef, a F-link of deadbeef, and a B-link of BBB null. So now if we did a show, probably get a crash. Yep, crash. Something to do with, yeah, can't resolve deadbeef. Cool, so we've got a read violation there. I'm curious, with this corrupted deadbeef, BBB thing, what if we try and set ZZZZ to XXXX? Do we get a crash because it's trying to write the pointer of the newly allocated entry for this to this node pointed to by this F-link here? Crash, yes. Do we get a write to somewhere near deadbeef? Nope, we got a read near deadbeef. That's still interesting. I think we're onto something here. So this here is the, it's a char star for var name. Gets nulled. Because we're keeping in mind that this as a replacer is actually a temporary stirdupe artifact that ends up getting freed. And I think the free is what's nulling out this char star here. Then this here is the char star for var val. It sticks around. This here is the, I'm calling it a record star, F-link. And this here is the record star B-link. And I reckon this fault here is because this dead beef is getting red when it shouldn't. I'm just going to make this be a whole bunch of A's. Actually, no, I'm going to make that B's. 42, 42, 42, 42. These can be A's. OX 41, 41, 41, 41. I reckon this dead beef here is causing the crash because the F-link's probably getting walked. Let's try again. So now we want to create a new allocation. Crash. Yep, it's dead beef getting resolved. So when we try to append something to our corrupted list, and just to recap, our corrupted list currently looks like this. A telly, oops, telly at BSS has a entry with the name being this and the value being that. And that looks kind of funky as well. That looks really funky. Anyway, here's the F-link. If we telly that for 4, then here's our corrupted entry in the linked list. This here is the F-link. I reckon it's getting walked when we try to add a... yeah, when we try to add a new record. What if we set this here to be the address of user is auth? Is it just going to cause some nonsense to happen there, or are we still going to be in crash land? So let's go and set the the record star of F-link to be the pointer to the user is authed value. See how we go. See what we get when we try to append to the doubly linked list. Oh, no crash. No crash. Now, let's have a look at the is authed value. Copy that. Examine it. Oops. Still null. What happened? Let's go and telly BSS again. Let's go and telly this. Did some shit get cleaned up, did it? Let's go break. Let's go telly BSS. And telly that for 4. Yeah, so the F-link is set to point to user is authed, but it's probably the case that because this here is actually a freed allocation, it's probably getting allocked and having stupid data be put there. Let's go and telly this for 4. Okay, a bunch of nulls. Now if we continue and just set Z to Z and telly that again. Okay, no, cool. The F-link's getting written. Yes, the F-link's getting written. So we need to go and subtract 8 from this pointer so that this pointer that gets written to .bss happens in the right spot. We're just off by a couple of D words, so we need to subtract 8 from this pointer, and it should cause this F-link to get walked across to BSS And then when we go and add a new thing to the list, it should just go and spew a pointer on top of the user is auth flag. As it did here, it was just off by a little bit. Let's try that. So now if we go and set Z to Z, there we go. We get the magic little hash happening. We can do help. We get the flag function. We run flag, and there's the flag. So that's how we exploit a use after free to get a really, really dirty write where primitive. We can afford to write a single pointer to the heap. Yeah, so we can write a heap pointer, and we get to control what is at that pointer. Yeah, because it'll be heap data. We may be able to use this to do some cool stuff. But the point is, what we can do is we can write a heap pointer to anywhere we control, based on having induced a corrupt state of the doubly linked list, and then allocking a temporary replacer. Actually, this with null's thing. Alloc a temporary replacer. I say temporary because it's the replacer that we end up being able to put on top of the freed allocation is a temporary artifact of stirdupe, and it is getting freed before stirdupe returns. But we can alloc a replacer. We set the f link to 0.8 bytes before the you are currently authed flag in .bss, and then we add something else to the list. Let's go and log adding something else to trigger the write where set new var a b. And when we go and create this allocation here, this f link will get warped, and then the pointer to this new record will get written at this address +8 into the new f link to kind of continue the list onwards. But this address +8 is the address of user is auth, and we can go and afford to write a pointer to some heap data at that location. So yeah, we managed to basically spike the user is authed flag, and then we can get access to super user functionality, run the flag command, and get the flag is the flag. So that's kind of cool. What have I missed in chat while I was busy on the home stretch? Yeah, no, Naxor. A lot of functions in the binary don't use the base pointer, so they just use EBP as a general purpose register. It's not actually a stacked base pointer. They do the whole optimized ESP thing where they actually refer to offsets from the floating ESP rather than set up a permanent base pointer for each stack frame. Nice work, Infinite. I wish actually, you know what? I've got chips. I was at a barbecue today and I brought chips, and not everyone ate my chips, so I brought chips home. So I'm having chips for supper. Thanks for sticking around, everyone. Do we want to see if we can continue on before I go to bed? I'm gonna just spend at least a couple of minutes thinking about what we could use this write where primitive to do. Because if we go and examine the user is authed flag in memory, it's this here. If we examine one string there, it's corrupted. Yeah, that doesn't look that interesting. Just give me a second. If we played with allocation sizes, we might have more luck at having something stick around there. Let's go A, B, 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 save that, do it again. Let's go and have a look at, whoops, not what I wanted. Let's go and telly that there. I actually want that as a pointer, you muppet. There we go. If we telly this, really? I really think that should be A's. I don't know if I'm seeing weird stuff like I was seeing earlier tonight. I'm going to try once more. Let's go and telly this here for 4. Yeah, that's what I wanted to see. So I can afford to write where a pointer to a record struct. So I can write a pointer to a string that I control. I can write a pointer to a string that I control at a location. What would I do with this? And NX is on, so I'm not going to just write a pointer to shellcode somewhere and away I go. I don't think there's a quick way to a shell with this one. If someone can see a quick way to a shell, let me know. That totally counts, Parks. Totally counts. Yeah, Zonoth 11. We've just finished up actually. If you're interested, check out the VOD, and I'll be uploading a copy to YouTube overnight tonight, which will be a better quality, higher bitrate copy because my internet can't push out any more than 2 megs per second. Check out the video. We've had a good night. We discovered and exploited a use after free bug in a it's actually Parks. It's a DEF CON quals binary. So the DEF CON CTF, there's a qualifying round, and there's a whole bunch of challenges in that qualifying round. If you win that competition, you can then go to the DEF CON CTF. So it's not a DEF CON CTF binary. It's just a quals bin. So yeah, if you're interested, Zonoth, then check out the archive. Done, you'll take it. So we can write a pointer to a string we control anywhere. Can we get a shell? Can we get a shell? What do the segments look like? What's writable? I don't think there's a quick way to a shell from here. If NX was off, we'd have a chance. And I could turn NX off for the challenge. But I could also just go to bed and get a good night's sleep. I think we're going to do that. I think what we're going to do is, because this is the last stream for the year, we'll end on a strong note. So we've managed to execute the flag function and basically elevate our privileges, which you can see here with the little hash. Based on a write where primitive from a UAF, which I'm pretty proud of. I think that's a damn good end to the year. Isn't the password in memory from before? You could set one of... yes, I could, Mongo. It's not a write what where though, it's a write where. Is it full rel row? No. I still don't understand how relocations work. I need to look into that. So Mongo, what it is it's not a write what where, it's a write where. What I've got so far is the ability to have a malicious f-link in the chain. Then I append a record to the doubly linked list, and then at this address -8, no, this address +8, which will be this address here, which is the flag in memory for the is-auth. I can write a... I'll show you what I can write. So at this address here, telly that for 1. I've got a pointer to a string I control. So it's controlled, but it's got a few levels of indirection. So if I was to use this to spike the GOT directly, then the GOT would contain a pointer to a string I control, and it is NX. So it's not a simple GOT spike. You could, old mate. Could you set one of the items to that and print it with show? Maybe. The issue is the replacer primitive I've got doesn't give me control over the first pointer in the struct, which is the pointer to the variable name. And if the variable name is a null pointer, maybe I can't get printing working. Good idea. Let's try it, old mate. Let's try. Mongo, I'll come back to yours in a sec. I want to see if this would work. Because at this stage we're already authenticated, so we don't really need to know what the password is. But at the same time, leaking passwords is fun because passwords get reused. So I'm just curious if we set this pointer, whoops, to the address of the password, quit. Now, if we do a show, will we get a crash or the password? Yeah, we got not a crash. But the issue is a bunch of garbage. BBB is E. No, because I think by the time we can actually do this show, let's get rid of this. Let's get rid of this set new var here to stop our replacer getting overwritten, and then do a show. A garbage BBB. Yeah, let's go on telly BSS. Let's go and examine the forward link as a pointer. Let's telly that for 4. Yeah, so there is a password to the pointer there. So this F-link, so the root node has an F-link to this with the password. But only the root node's being shown. So I think because this pointer here, this char star, is null, then it's not printing out this entry, because it thinks it's a invalid entry. And the replacer primitive we've got, because it's only temp and it gets freed, which I think is what's nulling out this pointer here, we can't actually replace at the moment. If we found a different replacer primitive, that could totally work, I reckon, old mate. In fact, if we go and spike this and set the int star that to be a pointer to the password and continue, and then do a show, then yeah, as long as we had a replacer primitive that let us control these two attributes of the replacing record, we could totally leak the password. Good idea, old mate. There's probably a couple of ways we could do that as well. That might be something for another day. So yeah, good thought. What if you corrupted the var-val instead? Yeah, so Mongo, the replacer primitive I've got doesn't give me control over both of those two char stars. The flag is not read to memory until you use the flag command, right? So Mongo, we've got the flag. We can do this. If I uncomment that, then the full exploit basically is a privesc. We've got a little hash here. We can do flag and access the flag function. I just wanted shells. So I'm not sure if that's going to give me anything, because it's not a whole record, and because my replacer is actually getting freed as well, it doesn't stick around long enough to make too much use of it. So it's a little bit fragile. Yeah, the password is read to memory. Yeah, so we're sweet there. I see what you were inquiring about. I'm just curious about something. Let me just try something real quick. No, if I reorder some stuff, that's not going to help me, I don't think. Yeah, I'm sure I could, Mungo. I'm kind of keen to go out on a high. I'm pretty happy with turning this UAF into a right-where primitive to at least be able to put a non-negative, non-zero value at this address here. So thank you very much, everyone, for sticking around tonight. I had a lot of fun. I reckon I'm gonna count that as a win. We wrote a cool exploit, and hopefully you've got a little bit of an understanding about the general nature of malloc on free, with the idea being that a programmer may want dynamically sized bits of memory that stick around longer than the stack. So you malloc something and you get a pointer onto the heap to go and chuck your shit on. Then when you're done, you need to be careful to free it again. Also, pro tip, if you're mallocing, then check that you didn't get a null pointer back, because if malloc fails, then I think you get a null pointer. Return value of malloc. Yeah, so malloc and calloc, on error, they return null. So always check your return values of malloc. So I hope you understand how that worked, and how the whole use after free phenomenon works when you have the ability to have a freed bit of memory still be referenced later on by the code. That's a UAF bug, a use after free bug. And if you go and craft, if you find your replacer primitive, go and kind of craft your replacement and kind of get it in there Indiana Jones style in the temple where you pick up the idol and you put something else down, then you can cause weird and wonderful things to happen upon future use of that inappropriately freed object. So I hope you understand the kind of theory behind it. I hope you enjoyed the practical side. I hope you enjoyed this year of streaming. We've been streaming for a couple of months now, and the fact that people want to stick around and watch me do my thing makes me very happy. And the fact that people say they get something out of it makes me very happy. So thank you so much to anyone who's stuck around. A very probably belated apology to anyone who I've been short with in chat before. I know I've been a bit of a dick to some people at times. I apologize. I really do appreciate everyone who sticks around, everyone who has suggestions, comments, questions, concerns. If I was ever a jerk, that is just my social ineptness coming through and my flusteredness sometimes from being on stream. I really do appreciate everyone sticking around, and I will see you all in 2017 for more of the same. Merry Christmas, Happy New Year, enjoy time with your loved ones. I hope you get some downtime. I hope you can recharge your batteries. And I hope you can enjoy your 2017 with me on this stream while I continue to be dumb. So thank you again, and I'll see you all on the flip side.